Okay, so our other material this week is dealing with modeling exponential growth and decay. Lots of things follow an exponential type growth. Population tends to grow exponentially. Two people have two people have two people, and so on. Lots of elements have a half-life or something of that nature. Carbon dating comes up because of the half-life of carbon. So we'll get some interesting problems out of that. So typically, I'm going to call these just to start talking growth and decay problems. And typically, there's a portion of that problem that says the population at any time t is proportional to the population, meaning there's some constant k that, given this initial population, if we know that constant k, then we can predict the population at any time t. So it's proportional to the population, right? So that becomes a separable equation. And again, I'm trying to establish a model is all we're doing. So if I divide both sides by p and multiply both sides by dt, then this integrates into a natural log. I'm integrating k's, my mistake, sorry. I'm integrating t's, aren't I? And k is a constant, so that integrates into kt plus some constant c. And I need to get p by itself because I'm trying to model population. So I can exponentiate both sides. And so I get e to the kt plus c, and that's what happened earlier. I can rewrite that as e to the kt times e to the c, and e to a constant is another constant. So we get this model that says the population at any time t is equal to some constant c times e raised to some constant k times time. And I know that there's lots of things at play, isn't there? There's a constant c I need to solve for. There's a constant k I need to solve for, and then I perhaps need to solve for time t, or I'm given time t. But that is my model for exponential growth and decay. So with that in mind, I'm going to set up a couple of these for you and then leave some for you to look at. Number one on the Lecture 8 handout says in 1790, the population of the United States was 3.93 million. So I'm going to let that be 0. In 1890, which is after 100 years, the population is 62.98 million. And then we want to know what the population was in the year 1900. Which is t at 110. So, and it's already been suggested to us to use this model. So we know that, actually, let me start with the model that we developed. And let me make use of this time equal to 0 to kind of establish that this is what we end up with, right? So at time equal to 0, there was 3.93 million, which implies that C is 3.93. So we get this P sub 0, that just means the initial population. That's going to happen every single time on these problems. So my model now looks like P at T is equal to 3.93 e to the kt. All right, so then I'm going to use the second bit of information to be able to solve for k. So I know that after 100 years, the population was 62.98. So I'm going to solve for k. And where's my calculator? So I can divide both sides by 3.93. So I get e to the 100k is equal to 62.98 divided by 3.93. 16.025, I guess is what I'll use. So if I'm solving for k, I need to get rid of this exponential. We've been getting rid of those logarithms by exponentiating. We're going to get rid of exponential by taking the log of both sides. So natural log and e cancel each other out. So I'm left with the natural log of 16.025 is equal to 100k. So I'll divide by both sides by 100. So let's see, natural log. Maybe I'll just use that whole answer in my calculator. Divided by 100. And let me use, I don't know, a couple of decimal places, maybe 0.0277. So now my model looks like P of t is equal to 3.93 e to the 0.0277 t power. That describes the population at any time t. In particular, I want the population at 1900, which is after 110 years. So 3.93 times e to 0.0277 times 110, and it looks like 82.73 will work. So the population is continuing to go up based on this model. If there's if something is decreasing, population is exponentially decreasing, or maybe it's a half-life or something of that nature, your k will end up being a negative value most likely, just because it's a decrease going on. Okay, so use that same model to set these up. I want to just talk about a couple of ideas here, and then you can go back and try those problems. Look at number 3. The radioactive material plutonium-239 has a half-life of 24,300 years. That means after 24,300 years, there's half what we started with. And it says if a sample initially contains 10 milligrams of plutonium-239, how much will it contain after 50 years? So you know that if I use this condition, that will allow me to set up and solve for C and then ultimately for K as well. Sometimes, knowing that this is my model, I know that there is half the population after 24,300 years. So you can actually divide away p sub zeros. I don't have to know what that is to be able to work with that. You know, in this particular instance, how much was there at the beginning, but I wanted to mention that to you, that I can use that idea and solve for k as well. The other option would be if there's 10 milligrams to start with, then after 24,500 years there is 5 milligrams. So I can actually put in the values. I can carry along a p sub zero. The math is going to work itself out regardless. The reason I mentioned that is on number 2, it uses carbon dating to determine the age of a fossil. And it says archaeologists believe that the age of the skull to be the same age as the campfire. That's not totally true, is it? But if a tree grows 100 years and a person lives 70 years over thousands of years, it's insignificant. So it's determined that only 2% of the original amount remains. So you can make use of 2% of the original. It's ultimately what you're trying to find. So you can set up using this idea of a half-life. We don't know how much was originally there. So we can set up that there's half of the amount after 5,600 years. So you can use that and not ever have to come up with a p sub 0 portion. We don't have to know what it is. We can do the math without that. And then you would want to solve, once you find k, then you'll want to solve for 2% of the original 5,600 times whatever k value you got there. Sorry, that's the half-life. Whatever k value, some k, which will be a number, times some time, right? And that's ultimately what we want to solve for. I never have to know what the original amount was because it'll divide away. But at any rate, I've posted solutions to those. So you have two models to work with this week. You have this exponential growth and decay model, and then you have the mixture problems with the in and the out business going on.